what we find is that for a charged particle to experience a force due to a magnetic field, first and foremost, there has to be motion. If I have an electron sitting on this table and I come up to it, ha! It doesn't even know I've got a magnet in my hand. If it's not moving, it does not feel the magnetic field. Now it's worse than that. It turns out that if I could create a magnetic field, a very strong magnetic field, pointing towards that open door, if I were to shoot electrons along the field or opposite the field, they would feel nothing. Absolutely nothing. Now, if you tried to shoot the electrons across the field, it's going to feel a force, and that force is going to be perpendicular to the field and the velocity. Now, look at this. If I have a positive charge, and it's moving that way, in a magnetic field that is that way. The force, the magnetic force, has to be perpendicular to this vector, and it has to be perpendicular to that vector. Now these two vectors define a plane, the plane of the whiteboard. And the only way that force can be perpendicular to both of them is if it is perpendicular to the whiteboard. So the only possible directions for this force are into the board or out of the board. It's going to be one of those. But you can see that if I draw the problem on your final exam on a two-dimensional piece of paper, the force is going to be out of the page or into the page, meaning these problems are all inherently three-dimensional. That's what you found with rotation, that all rotation problems were inherently three-dimensional.
Why does it the light go down?
We're getting to that. We're getting to that. I'm almost there. The question was, why did the beam go down? I'll show you. What's that? If it were positive charges, it would have gone up. But they were negative charges, so they went down.
What? No, that was exactly what I said.
Okay.
I didn't like the explanation.
Oh, I didn't hear the explanation because I don't have my hearing aid, so I just saw your lips moving.
You're good. You're
Okay, thank you. Just nod. It's what you do with tourists from out of town. Okay? Now, before we finish talking about the direction, let's talk about the size. We find that this force, magnetic force, is proportional to three things: the perpendicular component of the velocity, the size of the charge in coulombs, and the size of the field. That means we can write it like this, where K is a constant of proportionality, and it's proportional to these three things. Now, we've defined the units of force to be newtons. We've defined the charge unit to be coulombs, and we measure velocities in meters per second. But we haven't yet defined a unit for the magnetic field strength. If we're careful with our choice, we can simplify this equation and make this constant of proportionality go to 1. And that choice is to measure the magnetic field in what are known as Tesla. If we measure them in Tesla fields, what we get is a constant of proportionality that's equal to 1.